So, good afternoon, everybody. Again, today is the last class. That is to say, this is the last regular class. We will have a final actual class on Tuesday. That's going to be the review. The review is as always. It's going to be driven by you. So this should be the point where you should all already have sets of questions, things that you would like for me to go over. I usually don't, during these review classes, I usually don't speak until you guys ask a question, which is sometimes becomes a game of Zoom chicken. So we'll see how that goes this time. So today we're going to wrap up our optics. What we did not talk about yet is wave optics. So let me describe what I mean by that. So up to now we were talking about plane waves. So we did really talk about optics because from the standpoint of these are electromagnetic waves, and then we described how they interacted with lenses and mirrors. And the way we calculated the image formation was very straightforward. It was just doing tracking the P and the C ray. By the way, in some books you'll also find F and some other rays, which are just the complements of those. You don't really need all four of those. Usually P and C ray are fine. So we did that, and that subject is called geometric optics, right? Because you just have this very straightforward geometrical system, and there's just triangles everywhere, and you make all sorts of assumptions about the way that these mirrors and lenses are shaped, and then afterwards you'll be able to figure out where the image forms, and if it's inverted, upright, real or virtual. Now, the thing we'll do today is we'll actually do optics where the object that the wave is interacting with has features on the scale of the wavelength. So why is that important? Well, that's when you really start to see things like diffraction and interference. So I will explain what that means, but just remember that this is just a very, very special subfield. We're not talking about macroscopic objects, big lenses, big mirrors. We're talking about tiny objects or big objects with a tiny hole in it. There are very real limits to what you can do with optics, and it has to do with the fact that you can't really you usually can't see stuff that is smaller than the wavelength than with the wavelength of the light that you're using to look at it. So there's factors of 2 and 1.22, and there's numerical apertures and everything. But roughly speaking, if something is smaller than the wavelength of the light that you're using to look at it, you're going to have issues being able to resolve it. So, for instance, I have this in my lab. When I look at something that is I look at these tiny little holes. They're half a micron in size, and I can barely see them in an optical microscope. You can sort of see where they are, but they have diffraction rings around it and everything. They don't look like an actual hole anymore. And so how do you then see stuff that's smaller than the wavelength of light? Well, you need to use different kind of microscopes, and that's an entirely different field of study. In the past, we taught a course. There's a course that I designed. That was me and somebody from chemistry, somebody from biology, and somebody from geology. We taught a course in advanced microscopy. So we would use different kind of microscopes. So for instance, scanning tunneling microscopes, that's the part that I would teach. So where you can see atoms on a surface using a very sharp tip and a tunnel current. The Professor Elena Miranda from geology would teach scanning electron microscopy, and she's an expert on that. And then Simon Garrett from chemistry would teach atomic force microscopy, which he's really, really good at, and he uses all the time. Atomic force microscopy is using a very sharp tip, but then looking at the repulsive interaction of a tip with a surface, and then figuring out what the height is. You can also get atomic contrast with that. And then finally, Dr. Kwok and Dr. de Millar in biology would teach confocal microscopy. So confocal microscopy is still, very much the cutting edge of what you can do with regular optical microscopy, but it's really, pushing the boundaries. So this is a long story, just to say that microscopy goes way beyond what we're talking about today. But this is a good starting point, starting to think about objects, how they interact with light when their sizes become comparable to the wavelength. And then afterwards, what do? Well, you need a different kind of microscope. Okay, so that's for today. We'll do diffraction and interference, single slit and double slits. And unfortunately, I cannot do this demo, but this is a demo that I always would do in class. I just don't have the space for it. So we would take a laser and we would point this laser through a little aperture with a little hole, and the hole would be either one hole or two holes. And then you'd project it on a wall, and the wall would be 10 meters, that is about 30 feet away, and you'd see this pattern of dots. And that's the interference pattern, but unfortunately I can't do that here. And plus I don't think that would fit on the camera, so you'll have to take my word for it that happens. So I owe you a demo. So if all things are back to normal, you can come back next year for an in-person demonstration, and you'll be able to get that. Okay, all right. Before we do that, so my glasses, just as an illustration of what we were talking about. So remember what I was saying. So it's thicker here, and it's thinner here. So it's thicker here, thinner there. So it goes thick, thin, thick in both directions. Now I have a little bit of a cylinder, or astigmatism. So the curvature in this direction is different than the curvature in this direction. And most of you will probably have it, but that's how you're supposed to look at these lenses. So that's a diverging lens. That's because my eyes are a little bit too far converging. So yeah, and now of course I've smudged up my glasses, so I'll have to live with that. All right, so let's talk about wave optics. Okay, so the thing we need to do is we need to start thinking what's happening microscopically to an electromagnetic wave. What's really happening from point to point. So for instance, we have a plane wave that's traveling from here to there. We'll have a plane wave. So these are our phase fronts again. And then there's, lambda in between. And then this thing is traveling in this direction with some speed. So it's traveling with some speed in this direction. Now, there's this thing that you should realize is that all these points in space, they're not necessarily connected. So we have this description of this wave that's moving from this point to that point, but really what we're supposed to do is say, okay, at this point in space, what is happening there? And then do that for all of these points in space, and then add all those solutions together. And then if we add them all together, we should recover the picture of a plane space. So really, let's look at what's happening here at this point. So at this point, it's actually, this point is seeing an electric and a magnetic field that alternate. And then from that point, radiate radially out, because that's really what it does. So there's actually these circles of phases. So it kind of radiates out because that's what these points in space do. Now, there's a similar thing happens here for the point right next to it. So it radiates out. Okay. And this happens for all of these points. And all of these points that are on this line, they are radiating in phase because they are being excited by this wave that's coming in. So they're radiating in phase. And then if you put them close enough, you'll recover the picture where you have a wave that's traveling from here to there, but it is supported by the fact that we have all these point radiators, all these points in space that are radiating spherically out. Now, that seems like a distinction without a difference. In fact, it actually makes life a little more complicated. But the reason we need this picture is because what happens when we put a little hole here? So let's make a hole. I'll make this use a thicker color. Okay, so making 2 holes. All right, so now this is a screen, right? And there's a hole here and there's a hole there. I hope that that's clear for everybody. Okay, so look at this point here. This point here is being excited by wave that's traveling here, but when it's emitting waves in this direction, it's no longer compensated and backfilled by all these points here, because these points are not receiving a wave anymore. So this thing actually starts emitting waves that are going radially out. And I'm not drawing the exact same wavelength, but you get the idea. And the same thing happens here. So come on. Get a proper eraser again. I don't know where my eraser went. I'll use this one. So this is a snapshot in time. So that means that these are where the nulls are. Okay. Now, what does it mean when these things are interfering? Well, that depends a little bit on what the underlying wave is doing. So let me just draw this just in case we forgot. So there's a sine wave here, right? So this is what the amplitude is doing. So that means that there's also a sine wave here. So this is where it's 0. This is where it's 0. Actually, in between it's 0 as well, but that's what it's doing. So that's what the actual sine wave is doing. So we've got a sine wave on this side, and let me just call it a red sine wave, and it's spreading out. And then we have a green sine wave. Green sine wave. Let me see. Okay, so that's what's happening. And then, of course, at some point later in time, infinitesimally, all of these sine waves will have traveled. But the point is that after this aperture, it's actually traveling radially out versus in a straight line. Okay, so so let's see if these lines are representing where the amplitude is 0, then that means that where they're both 0, you will still get a 0. So for instance, this point here, the net field, both the electric and the magnetic field, will be 0 because both the red and the black field will be 0. When they are let me see if I can draw that. So no, I think I should use actual colors now, like a person. Okay, so this is now the green, the next front, and this is the red, the next front. Okay, so where they intersect is where you get a null. So it still stays here, 0. Now the question is, what's happening in between? Okay, so let's say that we have some point, and we have a, if we look at it as a snapshot. Okay, so let's say we have a green wave that does this, and then a red wave that does the same thing. Then the net field is going to be the sum of those two. So the net field would be just double, right? So there you go. If instead, let's say the green field is doing this, and the red field is actually shifted, so I'll draw it. So it's shifted by half a wavelength, then the net field is actually 0. So this is, you should know already from wave, studying waves, this is what we call constructive interference. And this is what we call destructive interference. Okay, so constructive because they add, destructive because they are subtracting. Okay, so where is that happening? Well, so this is where we have the constructive interference. This is also where we have the constructive interference. Then in between is where we would get the destructive interference, because then they have a wavelength out of phase. Okay, so there's a, now I'm running out of color. Oh no, I have blue. Okay, so this is constructive, and this is where it's destructive interference in between, right? Okay, so we could do this for all points in space, but usually we're not really interested in what's happening for all points in space. We're usually only interested in what happens once these waves hit some kind of a detector. Now the classic detector that we will use, and everybody uses, is just a screen. So just a projection screen. I'll just draw this here. All right, so that is a screen. All right, and now for every point on this screen, we need to determine what's the green wave doing, what's the red wave doing, and if they interfere constructively, we will find a peak, so therefore we will find light. If they interfere destructively, we will find a black spot, dark. And that is a function only of the distance. So let me show you what I mean by that. So for instance, there's this, see, my ruler is not long enough. Okay, so there's this path right in the middle where if you ask what's the distance from here to there, it will be the same from here to there as from here to there. So therefore, because the distance is the same and these are hit at the same time because it's illuminated by a beam of light that is coherent, so there's no phase difference between these 2 points, that means that if the path difference is the same, that also means that the amplitude here is going to always be the same. So at this point, you will find constructive interference. All right, so it will be AKA light. Okay, now if you move away from here and you go up, at some point you will get destructive interference, and then you will get constructive interference. So what do I mean by that? Well, let's see. So for instance, if we go from here to there, and from here to there, the path lengths are the same. So this, let's call this L. Actually, let me just use colors. So this is L, and this is L. So green L and red L, and because they're the same, they interfere. Now here, and here, the length difference amounts to half a wavelength. Okay, so this is L. Let's call it LR in case people are having issues with the either color blindness or some black and white issues. Okay, so red, this is green. Okay, that's G. Okay, red and green. So they're not different color. I'm just using that to indicate where it's coming from. So at this point, LR minus LG, or rather LG minus LR, that's here, is lambda over 2. So that's why we get destructive interference. Okay, so the path is now, if we want to know where these spots are, we need to find what is the path difference from here to there, minus from here to there, or the other way around, as a function of the height here. And then when that path difference is half lambda, then it's destructive. And if it is lambda, so by the time here we are back to lambda, so here it's lambda. So this is lambda, this is lambda over 2, this is 0, and then here we will find minus lambda over 2 if you want to be consistent in your signs. So minus lambda, right? So you'll get a bright spot, dark, bright, dark, bright, dark, right? Or in other words, on the screen you see bright, 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 bright. Okay. So now the question is, what is delta L? So okay. Now this is usually an exercise that I have you go through because it's actually it's a good exercise. So I'm going to do that, but I'll set up the coordinate system for you. So you need to know a couple of things. The first is that you need to know this variable, right? So this distance from, this is L, is the distance from the this thing with the two holes in it to the screen. So we're going to call that L. We're going to use y as a variable to measure the distance from that midpoint up. So this is y is equal to 0. All right. And then we need to know also what this distance is. And we're going to call that distance, we're going to call that d. So d. Okay. So we want to know delta L as a function of y and d and L, right? So it's going to be and then we want to solve for delta L as a function of y. Okay, so I'm going to go and, so for those of you that are looking at this in the recording, I will put I'll write down a hint and then I will pause it. So I might go faster in the video than you want, so you could just pause it yourself.
Professor, are you still muted?
All right, ladies and gentlemen. That was quite the ride. Okay, so let me walk you through what I was doing. Hopefully you're all kind of following along. I like doing these kind of exercises with you guys scribbling along, because I think if I just do it as you're watching and just observing what I'm doing, you're not actually seeing what it is we're doing and also why. So when you see that I'm saying assume that D and Y are much smaller than L, you should have this Pavlovian response that you're probably going to need a whole bunch of Taylor expansions. Now, the tricky thing about this is that you actually need two. You have two of these, so you have to figure out a way to make things go. So the first setup is just a geometry, right? So this is a right angle triangle. So going from here to there, that's a right angle. So in other words, any point on the screen here that's measured by Y, we can measure the length from here to there by just using this as the base of the triangle, and then Y minus this height of D over 2 as the vertical, right? So that's why you're getting Y minus D over 2 squared as the vertical, and then L squared as the base. And then that's your red length. And then the green length is the longer one, right? Because it has a triangle that's longer, that's taller. So that's the one that has a positive. Now, delta L is LG minus LR. And the thing that makes it tricky to do that is because of all the squares and the square roots, right? So if you want to subtract these two, you have to look kind of carefully at what's happening here. So the only way in which these expressions are different, so when you subtract them, the only way that difference shows is the sign of this thing. So we need to rewrite this expression into something such that this thing is linearly proportional to something that carries that sign. So we need to figure out a way to pull that out of the equation. So that's what the assignment is. So the first thing is you expand, so you just write it out. I like doing this because then I don't need to do it twice. And then you see, because they're only different by a sign, so you can keep track of where the sign is going. So first you just square it out, and then this is where the first approximation occurs. So this is obviously the smallest term. This is the biggest term. You don't want to throw everything away, right? Because if you throw everything away, all you're left with is L squared, and then your path difference is 0. So you need to keep L squared plus whatever you can to get something that is slightly different for the two terms that have slightly different signs. Okay, so this is the one that is the smallest one. You can actually keep carrying it, but why would you do that, right? Because this is d squared over 4, and this is yd. This is definitely going to be the smallest one, because actually y is usually measured in centimeters and d is usually measured in microns. So we're going to drop that one. So then you have to work this into something of the form 1 plus something. So the canonical Taylor expansion I'm going for here is this one. So if you have something as 1 plus x, you can approximate that as 1 plus x over 2. So I want to rewrite that term in this form such that I can use this Taylor expansion and get rid of my square root. Because if I can get rid of my square root, I can subtract the terms. Okay, so that's the point. So I factor out my L squared plus y squared, because that's the thing that's the biggest one, and then yd is much smaller than L squared plus y squared. So this term is much smaller than 1. So it's already of this form, 1 plus x. Okay. Then what I do is, this is bigger. So in this L squared plus y squared, I don't need the y squared anymore, because this thing is going to dominate the denominator as well as under the square root. So I'm going to drop those two. Okay. Then the next thing I do is I'll say, okay, well, now I have this, and I have it of the form, of this square root form. So all I need to do is just write it out, drop the square root, put a factor 2 here in the denominator. Okay, so now we're home almost. Now delta L, that's the path length, right? So it's still that original expression, but now we have this simplified expression. So first we use this form with the plus, and then we use this form with the minus, and we subtract them. And you see that when we subtract them, these terms with the 1 that multiply L, they're going to drop out. And these two terms, they're actually going to add up, right? Because you have a plus and then a minus minus. So these will be minus minus plus. So you just get double this term. So you get yd over L squared, but you still need to multiply by L. So you get yd over L. So finally, after this Herculean effort, we get y, that's the height, is L times the path length divided by the distance between the slits. Okay, so far, we haven't actually done anything optically with it. So far, this has just been a quite tedious study in geometry. Okay, so we haven't actually done anything with it. So what do we want to do now? Well, remember what I was saying. If the path length difference is lambda, then you get a bright spot. If it's half a lambda, then you get a dark spot. So in other words, if it's 0 lambda, 2 lambda, then you get bright spots, right? So we get bright spots when delta L is m times lambda, where m is 0, 1, plus minus 2, etc. Okay, so therefore we get bright spots where, so y is L m lambda over d. All right. So what does that mean? Well, if let's say we call this 10 meters, we take a distance of, let's call it 10 microns, and let's call lambda 500 nanometers. Then you get delta y, or y, well, let me see, that's 10 meters, 10, let me see, that's 10 times 10 to the, it's 500 nanometers, right? So that's a -7 times 5 divided by 10 microns. So that's a 10 minus 5. Yeah, so equals -7 minus 5 or 10. Yeah, a couple of centimeters. Okay. Anyway, so you get something in the order of tens of centimeters or something. So it depends obviously on the distance, right? So if you place these two apertures, if you place them instead of 10 microns apart, you place them 100 microns apart, then this interference pattern is going to be spaced by peaks that are separated by a couple of centimeters. So why all this stuff? Well, the cool thing is that now if you go in and you do this experiment, so you do this with a laser, right? So you have two slits in a screen, and you shine a laser light on it, and the laser is coherent, which means that this point and that point, there's no phase differences between them. So the laser light, as far as these two slits are concerned, is considered a plane wave, and it's monochromatic, one color, right? If you have a red laser, it's really red, no other colors in. And now you just measure the distance here from here to there, and you measure how many bright spots you get in a centimeter. You get your distance in Y, right? You get your distance in Y, and then you know what L is, you know what D is, presumably, because you know what those slits are, and you can solve for lambda. So that's how you can measure the wavelengths of light. And usually when we do this in class, it's usually pretty accurate. Usually get it down to even with quite a lot of simplifications, you usually get it down to at least 10%, if not better, because that's usually limited by my ability to gauge how many meters it takes to go from the board to the wall. Well, this is a paper from 1999, so not too long ago. So they did this experiment where they took this oven, and then there were these Buckminster fullerene balls coming out. So these are C60 molecules, and then they used the diffraction grating just like those slits that we were using. And then lo and behold, what they looked at the counts, and they found like a peak and a peak and a peak, and that's because particles also have wave-like behavior. And for C60 molecules at that time, that was the biggest record. People had done this with electrons before, but not with anything as big as 60 carbon atoms. So it's quite crazy that works, and it's a beautiful experiment. Anyway, it was 20 years ago. Okay, so this is double slit interference. Now we need to talk about what happens with a single slit. Single slit is a little trickier because we start with the same situation, but now we're going to incorporate the fact that these slits actually have finite size. So even for a single slit, you can see interference patterns. So how does that work? Well, so let's say we have a where's my screen? So this is the aperture, right? So it's a single slit, and now there's a wave that's hitting it. And now before, we were assuming that this point here we can assume as a single point, because we treated this as like a point emitter, and the interference pattern that we got was basically because this was interfering with the light that was coming from the other one. But now we need to actually consider there's a point here, there's a point here, there's a point here, there's a point there. In fact, we need to consider all points in here. So in other words, when we do this when we do this calculation, we get an interference pattern that looks a little different. Okay, so if you look at the distance from the aperture to this point, there are waves coming from here and from here and from here and from here, right? So we need to add all of those up. Okay. If we do the same thing here, let's say some point here, so we'll do here, here. So we're going to add all those together. So in other words, the top one with respect to the bottom one might give you a contribution of this, because the path difference might be lambda. But anywhere in between, the path difference could be a fraction of that. So what you end up having to do is integrate over all those paths. And that means that you have to integrate over a sine wave. So that means that when before you would think that this would give you constructive interference, because between the top and the bottom there's exactly one wavelength of light. The problem is that all the stuff in the middle basically cancels that out. So the first time you see a peak is here, where m is 3/2. So then the integral of all those paths no longer amounts to a sum that is 0, but it gives you a sum that is non-zero. So this one is then dark. This one is light, because it doesn't integrate out anymore. This is dark and this is light. So it actually adds 1/2. So the equation is still the same. So it's still y for bright is still the same path difference, except now we're actually integrating it. So it's actually m plus 1/2 lambda, and now over w, where w is this width. All right. And that's how single slit interference works. So now, how do you put these two together? Because before, when we were looking at double slits, we kind of swept under the rug that these slits also had a finite size. So really what we need to do is we need to recognize that in addition to having an interference pattern that looks like this, we will also get an interference pattern that looks like that on top of it, but it's usually spaced bigger distance, right? Because the width is the thing that sets the scale. And here, the distance between the slits sets the scale, right? So usually the width is much smaller than the distance. So you'll get a rapid pattern for the double slit effect, and then you get a slow pattern for the other. Yeah. I do apologize. Actually, it's light here, it's dark here, and it's actually light here in the middle, because it does not integrate out. Because you have the path from here and there, they actually add up. Sorry, this is light. There we go. So putting it together, you get an interference pattern as a function of y. It looks a little bit like this. So you get a rapid interference pattern. And you get a slow interference pattern. Okay, so this rapid pattern is due to the slits, to the two slits. And the slow pattern is this envelope And this is due to W single slit. All right, ladies and gentlemen, that brings me to the end of the lecture part. And promptly I destroy my setup. Brings me to the end of my the lecture part of this class. So study hard. It was my great honor to teach you all and to have you in my class, and I appreciate all of you that were hanging in there until the last moment.